of an experiment. I was discussing with Tibra about a conference or a workshop I was at last week in Vancouver called Testing Gravity, which was really loads of fun and extremely interesting because it brought together not just people from one community, brought together theorists, or sort of really hardcore theorists, extreme theorists, sort of more modeling type theorists, as well as people doing real experiments. So it was actually quite an interesting environment, and particularly with this being 2015, I thought it might be fun to just have a more sort of discursive type of class just talking about these experiments. So naturally, as I go sort of sitting, after dinner last night thinking, oh, I'll pull all these slides from this conference, not only was the internet not working in my apartment, as usual, but of course, now that I've got in here this morning, coming in a bit earlier, I find that in fact not everyone's put slides on. So anyway, the idea is I'm going to sort of talk about a few things to do with Einstein gravity, testing it, ways in which we can test it, or going beyond Einstein. So there's going to be bits of formalism to start with, and then hopefully, technology permitting, my hastily constructed set of slides, which I've either poached from this conference or else tried to glean bits and pieces where someone hasn't put their presentation on the website. So that's the idea. So hopefully it'll be a bit less of an intense lecture than usual. So why would you want to change Einstein gravity? Why would you want to go beyond Einstein gravity? I think, there's sort of several answers that you could give to this. I mean, there's the because it's there type of answer. That's the theorist's answer. And then from an experimenter's point of view, I think the answer's fairly obvious. If you're looking for something and you only look with one particular lens, then, if you have a hammer, everything looks like a nail. So if you've only got one thing, how do you know that what you're seeing really is that one thing unless you look and test it against alternatives? So it's good experimental practice to have alternatives. So when they modeled collider black holes at the LHC, that was not because people really thought that switching on the LHC would start up a black hole that might gobble Geneva and then the rest of us. It was simply because you're switching on a new machine at new energies, a new experiment. You have to be sure that if something crazy happens, you've at least got some things on the shelf, some templates that you can go and compare your experiment to. It's good sense, it's good practice, even if sometimes theoretically people think you're a bit crazy for doing some of the things you do. So I think the biggest motivation, so why So there's, from the pragmatic side, I think the biggest motivation for trying something different comes from cosmology. Now, I've been a bit torn about how much to say about this, given I know you're having a course in cosmology. So I decided I would discuss it a little bit, but maybe not go in, not derive things in detail. So this will be something that if you do the cosmology course, you'll see in detail. If you don't, then at least you've got the sort of key points. So what's coming from cosmology? Well, to make our standard cosmological model work, everybody says, oh, it's very simple. It's lambda CDM, which means lambda is, of course, we know, a cosmological constant. So that's, let's say, about 70% of the universe. And CDM means dark matter. So you're looking at sort of, whatever, 28% or so of the universe. I'm probably going to get my percentages wrong here, but I'm just trying to get a sort of sort of broad brush, I'm going to call it 25% here, and then I'm going to call standard model matter. What that means is that the universe that we know, I hope I've got my percentages right, is actually a tiny percentage. Now, if you come up with a theory, everybody's sort of so happy about lambda CDM, but the fact of the matter is it's telling us that about 95% of the universe is stuff we don't know how to describe within a consistent quantum field theory. So that really should be embarrassing. And we really shouldn't be sort of saying, oh, it's cool, we don't need to modify Einstein, okay? This really is a question and it's a challenge. The other reason, of course, from theory is that if we believe string theory, then we have extra dimensions, we have moduli or degrees of freedom from these extra dimensions. Now, you know, there are plausible mechanisms for stabilizing these, but these still tell you that we are beyond Einstein. So there's plenty of reasons why we should at least think about doing something other than Einstein. So let me just wanted to say a little bit about this dark energy, because this is one of the things I haven't put a slide on. So the dark energy issue, this is the lambda issue, right? We've kind of, I think, come to terms with the notion that there's some dark sector out there with properties like matter, because that's not so hard to fit into just a little bit beyond standard model. Although again, if we keep on not seeing supersymmetry, we might worry a bit more about this. So in cosmology, we take what we call a Friedmann-Robertson-Walker universe, and our universe, I think I was saying this in words previously, our universe is extremely simple. It's just a cosmological time, a scale factor, and then a homogeneous space, homogeneous and isotropic. So this is a constant curvature. So we have k is 1, 0, or -1, and these tend to get called closed, flat, and open. So this is your sort of 3-sphere, r-cubed, and the hyperbolic. So that's like an anti-de Sitter type of space. So we have our Friedmann equations, which you'll be seeing. So we have a perfect fluid source, which means we have an equation of state. A pressure is proportional to energy density. So this is cosmology in a nutshell. And from this, when I claimed we could go right back to the first sort of fractions of a second, this is the broad model that will take us there. So our universe tends to have matter. So this is what we might call dust, P equals 0. Radiation, which not only sort of has a volume factor associated with the way it behaves, but also a redshift factor. So this is W is 1/3. And then our lambda, of course, is a to the 0, and that's W is -1. So we build our cosmology out of those basic building blocks, those basic solutions, or the lambda CDM cosmology. So what happens? Why do we believe there's a lambda? Well, we sort of rewrite our Friedman, and we say that we've got our sort of h squared, where h is a dot on a. We write it as the sum of what we call these omega parameters. So omega is like a fractional density. So omega I is sort of 8 pi g rho. So we sort of say that our sort of expansion rate is the sum of effects from the matter, from a cosmological constant, from radiation, and also actually from curvature, just to make things sort of consistent. So, at the current time, our omegas sum to 1. So that's the idea, and we can split them into matter, radiation, whatever else, curvature, etc. So we end up with this picture, and you see that power law behavior. I should also say this Z. So you'll get a lot more detail, obviously, in cosmology course. Z is a parameter we use to measure cosmological distances. The further away something is, so if something's a distance away from us, this a squared, the scale factor, means it's receding from us. So Hubble sort of really nailed this in 1929. And so it's what we use to measure distances at very large cosmological scales. So that kind of explains what that thing is. And then what's been done we have to be able to decide how we calibrate our ruler of redshift. We have to be able to say, this object with that redshift is so-and-so megaparsecs away, so far away. And the way that we do that is we have to have an alternative distance measurement, and that's the sort of notion of standard candles. It's the further away something is, if you were in a sort of standard static Euclidean geometry, the intensity of light would fall off like 1 over r squared, because the light spreads over spheres which have area r squared. So this is what the supernova surveys do, but there's a slight sort of wrinkle in that what they measure is the luminosity, and because things are moving away, their light is redshifted, so the energy obviously goes down, and there's a sort of additional time dilation effect. So this is what they measure, and we can relate that to an integral of our a dot on a. So that was why I wrote it like this. So what these large-scale, or these high redshift surveys do is they start to populate an expansion history of the universe. So clearly, to sort of leading order, this distance is just linearly proportional to z, redshift. But as we go away from leading order, we start to get information coming from that h, the dependence of h on z. So what the supernova surveys found, or published in the late 90s, was the fact that these supernovae were fainter than you would expect if you had normal matter. So your omegas, your H was kind of scaling with redshift like 1 plus Z cubed. So the supernovae were fainter than expected, which meant the universe was accelerating, which meant, if you sort of look at this, this dependence on the omegas, that H has an omega with a negative equation of state. So a negative equation of state is something where you've got a tension, not a pressure, and that's like a cosmological constant. Now, the cosmological constant is an extremely good fit, but again, if you're looking for omega equals -1 and you only look for W equals -1, that's what you're going to find. And so it's quite possible to instead introduce something with an equation of state. Well, in fact, it's even consistent to have omega slightly more than -1, but not so comfortable theoretically. We can have an equation of state, therefore, that isn't exactly the cosmological constant. So that's really why cosmologists call this extra acceleration term dark energy, because it's trying not to be specific, saying it's a cosmological constant. Because yes, data is consistent, but it's not proven. And it may well be that we can never actually say with the sort of level of confidence of like a particle experiment, that indeed W is -1. So that's the story about dark energy. And to link it to things that we've been discussing in lectures, how might we get this? Well, we can either sort of change the left-hand side of the Einstein equations or the right-hand side. So let me just give a little discussion, a little bit of theory here, about some models that at least try to deal with the problem of acceleration by using scalar fields. So I'm going to start with something which I think you saw a bit in tutorials, so I'll be a bit sketchy with it. But I want to then extend the discussion to actually including a particular mechanism that I think is quite interesting, even if it may not work. So I believe that you did a tutorial on Brans-Dicke gravity, which was a scalar tensor theory explored back in the sort of early 60s. The notion behind Brans-Dicke gravity was a sort of Mach's principle. One of the things that bothered Einstein about his equations was that in the end, he was by hand putting in the relation between energy, momentum, and geometry. So it wasn't like it emerged from the theory itself. And another way of thinking about it is how does an inertial object, how does it know when it's accelerating? Yep.
Should there be a square in the denominator of the last?
No, I think that's correct. As it stands, anyway. This is just the original. I'm just using this to motivate a sort of later discussion. So So how, if you're accelerating in empty space, how do you know what you're accelerating with respect to? It's that notion. How do you know you're accelerating? And so the idea of Mach's principle was somehow that it was the universe provides a rest frame. Now you see that a bit with Friedman, Robertson, Walker, but it's a bit stronger than that. It's this notion that all the other masses in the universe provide the sort of background against which you're accelerating. And so here, this is sort of summed up, as we'll see, by phi is taken over the place of Newton's constant. So phi is like sort of related to Planck mass squared. So what we're going to see is that, at least notionally, having other matter in the universe gives a background phi field, and therefore gives a background Newton's constant, gives a sort of a sense in which we know how things gravitate. So you derived, hopefully, the Einstein equations, which you could write in this form. So here I've just written the gravitational part of the action. So you get your Einstein tensor from this. And so this phi, again, is sort of 1 over phi is like Newton's constant. If matter's there, you've got a matter energy momentum. But then you also get a pile of terms involving phi coming from the integration by parts here and the variation of this piece. So this T phi is terms which involve derivatives of phi. So this is the standard brand sticky, or something like it you'll have seen in tutorials. And the idea here is that the scalar field couples to the trace of the energy momentum. So it's coupling to other matter. The more matter there is, the sort of stronger the scalar field reacts. So Newton's constant sort of depends on what else is around. So although that sort of might be philosophically a very nice picture, it comes into difficulty when you start putting it against the real world. Because if the scalar field is reacting to matter, that means in our solar system it's going to react to the local density environment. And so that means, or putting it in a particle physics way, it means that you've got scalar forces. So you have fifth forces. And so this is pretty strongly ruled out by solar system tests. Omega has to be so big so as to suppress the coupling of the scalar field that you might as well just put in Einstein gravity. But what I want to just discuss now is quite an interesting mechanism which allows you to have a scalar tensor theory, but manages in denser environments like our solar system to suppress interactions with the scalar. So this is called screening. So that's what I'm going to just quickly discuss now. So I'm going to take something that's very similar to Brans-Dicke, but just slightly different. So we're going to sort of have a Brans-Dicke-like theory where we're going to sort of replace phi with some function of a different scalar field, phi, and we're going to go to the Einstein frame. So remember when I was doing Kaluza-Klein, I discussed conformal factors and how things could look different depending on what frame you're in, and we're going to see that here. So notice that in this frame, if I take the covariant divergence of G, I get 0, which means that on the right-hand side, it doesn't mean that the covariant derivative of the matter energy momentum is 0. So things do look a bit weird there. So in the Einstein frame, my Einstein frame has something that looks sort of familiar. This is our gravity sector. So you can see I've renormalized or rescaled my scalar field so that even though it's coming from the gravitational sector, it looks like a canonical scalar field with a canonical kinetic term, a half grad phi squared. I've got a potential, so you can see that that's a bit different from Brans-Dicke, but this sort of looks Brans-Dicke-like. Now, in the matter part of the action, this is just heuristic. What this is meant to emphasize is that previously the matter Lagrangians just look like standard matter Lagrangians with a standard metric, Jordan frame metric. Here, this is in the Einstein frame. Matter couples directly to the scalar field through the conformal factor. So you've made gravity look good, but you've kind of introduced some strange couplings, in the matter sector. And the reason for that is that you still have to preserve some of the features of the Jordan frame. So if the divergence of T was not 0 in the Jordan frame, you're still going to have something similar happening in the Einstein frame. So the scalar equation here, we start off with what we would expect for an equation of motion, wave operator, gradient of self-interaction term. But now we've got this a squared term in here. So we get also, if we just, let's say, have a row, so if I assume like a cosmological density fluid, and I rescale my components of the fluid density so they look like what I would interpret as a proper energy density with the right scaling, this is what I get for my scalar equation. I think the key thing here is not to worry too much about what's, about the details, but to kind of look at what's happening. What happens is our scalar equation now is not just from the potential, it also has an additional interaction which is density dependent. So this is where this notion of screening comes from. If we sort of sketch our potential V of phi, we could have a rolling potential, which, if it was just on its own, would give acceleration. But then, so this is V effective, this is V, this is the A-1 rho term, And so you have, as always, I'm pretty lousy at drawing. So the denser the region, the stronger the lift is in the effective potential. And so you see that round here, the mass m2 squared, or this mass effective, is bigger than the effective mass in the right-hand side. And so this is an example. This was called the Chameleon. And it's a simple example where I can get across this notion of screening. So the idea of the screening mechanism is that because you have some sort of scalar which comes in the gravity sector as a scalar tensor theory, so you have a conformal factor which is dependent on your scalar. If you look at the physics in the Einstein frame, your scalar field, well, it still couples to the trace of energy momentum, so we're harking back to the Jordan-Brans-Dickey theory here. So there's always this trace term, but this trace term is giving you something that depends on the density of the environment. And so it's possible that you have an effective potential such that if you're in the galaxy or the solar system, the ambient density is sufficiently high that your scalar mass is sufficiently high not to disturb solar system tests. However, on a cosmological density scale, something more like this, the scalar mass becomes sufficiently low or insignificant. You can see here you've got sort of an effective cosmological constant, such that your solution is more like a rolling scalar field which has accelerated expansion. So that's the sort of gist behind one set of theories that modify gravity. And as you see, by modifying gravity with a scalar, you do have to be careful that you don't get into trouble with various known tests of gravity. So other ways of modifying gravity, I'm just going to sort of list them here. Oops. Well, there's actually there's loads of ways of modifying gravity. Probably the first one, which you may have heard of, is this is not so much modifying gravity, it's modified Newtonian dynamics. This was to try and solve dark matter. We don't tend to think this is correct now. Probably not, because of an observational sort of bullet cluster. This was an observation of two galaxies that had recently passed through each other, and you can see the luminous matter. You can deduce the dark matter from a sort of lensing type of profile, and it looks very much like there really is dark matter there. It's not as if it's a modified dynamics. The luminous bits have interacted, the dark matter bits have not. So that's the simplest one. In terms of things we've been doing, we modify Lagrangian. So there's loads of ideas here. There's things where you add arbitrary functions of the Ricci scalar. There is things called a sort of Gauss-Bonnet type term, which is involving the Riemann squared, Ricci squared. I think I've got the right factors there, doing it from memory. So the Gauss-Bonnet term does not introduce any new dynamics in 4 dimensions. It's a topological invariant, but again, if you multiply by a scalar, you've got something with dynamics. So you can get all sorts of extra pieces involving combinations of these different curvature invariance. The problem that you have to bear in mind is that if you don't have second-order dynamical field equations, then you tend to have ghosts. So you have to be a bit careful about dynamics. We've also got massive gravity. Things, Galileons, Lorentz violating gravity. There's really a huge list. So I have by no means been exhaustive here. I've just tried to sort of give a bit of a feel for certain things that you can do to modify gravity. So how do you test some of these ideas? Well, actually, this cosmology can prove quite constraining. We've got things like structure formation. Excuse me. So in structure formation, this is how structures form in the galaxy. Obviously, that could change if you modify gravity. So this is tested via large-scale structure surveys and numerical simulations of structure formation. Stepping back, we've also got, just more generally, the evolution of the perturbation spectrum. So that's sort of explored in the CMB, and again, we've got to have numerical simulations. So that's CMB, FAST, or whatever they are, your favorite code. So this is actually quite constraining, as well as making sure that you don't screw up with the supernova, the sort of more recent expansion history in solar system tests. There are other things that you might not think about so much, but for example, with these screen scalars, because you have these extra scalar forces, you could imagine, although in an environment like the solar system where you're looking at relatively low energy effects, you could imagine inside a star you're at a much higher energy. Is that a problem? So people have thought about looking at the main sequence stars, seeing if they're changed with scalar interactions, neutron stars, pulsars, black holes, etc. And in fact, something which I've got a couple of slides on, screen scalars can also be tested, or at least people are proposing to test it by atom interferometry. So I'll come back to that when we get to the slides. So the last little bit, and it really is a tiny bit of theory, a few equations I'm going to put up. I'm just going to pick on this business of black holes because, you know, I think what I want, my slides, you'll see, are focusing on not so much on things that we already know, like solar system tests, but where is there going to be a big development in the near future? So just a few equations here. You might think that imaging from a black hole is a contradiction in terms because it's black and nothing comes out, okay? But that's not true because a black hole can often be in quite an extreme environment. It rarely forms in a vacuum. There's usually a lot of stuff around it. And all the while, it's sucking this stuff in. And when things fall into a black hole, they get dramatically squashed and pulled apart by tidal forces. And this leads to sort of quite a high energy environment and emission sort of all the way through the spectrum of electromagnetic radiation. So one of the things, you know, we sort of do all this stuff with geodesics, and you kind of think, oh, yeah, sure, I know what a black, you know, what this environment looks like. But there's some quite interesting effects that come from the way the geodesics escape from the black hole. So this light, which is what we're observing with, can have what, let's just say, an interesting path. So I'm just going to motivate, so this is some of the pictures, there's a little movie which hopefully will work. So just to recall from the lecture I did on Kerr black holes, our effective potential, and I'm going to now say for Schwarzschild and for a photon, is the following. So it's quite simple. This is our effective potential. And remember, r dot squared plus this effective potential should be 0 for the geodesic. So this is obviously a simplification. I'm just trying to sort of get the key feature across. So if I look at, let's imagine we've got a photon that's initially tangent to the black hole. So this minimum radius, I'm imagining this photon's coming out, so obviously it's a minimum radius. And this is what it satisfies using our effective potential. So this is like an initial condition. So h squared if I start off saying what happens, you know, so this would work if something was sort of flipping down into a black hole. It's also sort of true for neutron stars as well. And so here, this is my h squared, and so my phi dot, which is equal to h on r squared, is something like 1 over root 2 gm epsilon. So just looking at that, without solving anything, okay, what that tells me is my photon, as it starts to move away from r naught, the scale of the potential there for r dot squared is 2 gm. So that sort of tells you about the rate at which r is changing. On the other hand, phi has got a 1 over root epsilon, which I'm imagining is fairly small. So what that means is phi is changing a lot more rapidly than r. And so what happens, if you like, is that the photon kind of hugs the black hole before escaping. So it sort of goes around and around quite a few times. So this sort of idea is called strong lensing because it's in no means a sort of perturbative thing. This is something quite dramatic, and it leads to interesting images. All right, in no particular order, I picked sort of three frontier things to sort of, I've filched the slide, so hopefully I'm not in any plagiarism trouble. You can see the credits to whom, credit is due. And so I thought I would just take these examples because I think this is kind of where some of the exciting stuff is going to happen. So the obvious one, the one that I've absolutely got to start with, is gravitational wave observation. So we've discussed gravitational waves at least tangentially throughout the course, and we also did the formalism of linearized gravity that you need if you're going to look at sort of sources from anything other than, some extreme events such as a black hole or neutron star merger, which has to be modeled numerically. But a lot of situations you can get profiles using that linearized gravity. So for LIGO, this is a gravitational wave experiment. So here's our picture. Let me get the hockey stick. I'll have the pointers here. Remember I talked about polarization states. So the sort of idea of LIGO is to measure these space-time distortions. That's just a general idea of a gravitational wave detector. And this is just giving here, of course, this is the LIGO lot. But they're also pointing out, I kept this because it also tells you where else you can explore gravitational radiation. You don't have to detect it directly in an experiment. There was a claim of detection of primordial gravitational waves, whereas what was really detected was a B mode in the CMB. We've got pulsar timing arrays. That's, again, a good precision test of GR, energy loss as things spiral in. We're hoping to start to do space-based interferometers, but at the moment, the LIGO is a ground-based interferometer. So here's a set. I thought this was a nice little slide. What you see from some of these slides is that observational astronomy is becoming very much a global science. Here are the LIGO, advanced LIGOs, in Washington State and Louisiana. Hope I've got the right states. This is an older experiment, but it's been upgraded, Virgo. GEO is, the 600 stands for 600-meter arms. I think it's 2 or 4 kilometers for LIGO. GEO was a small experiment in Germany looking for gravitational radiation, but they managed to get, because they had such small sort of interferometer arms, their technology of the actual sort of detection was very good. So these guys merged with those guys. So they kind of collaborated with their technology. And India is proposing also to build a gravitational wave detector, and indeed this one in Japan. I think it's Japan. So this is the sort of idea, a bit like Michelson-Morley, but a bit more sophisticated, obviously. 4 kilometers, phew, got it right. And so the idea is that you're putting, lasers in this. Imagine evacuating a cavity 4 kilometers long in a vacuum. So it's just the same basic thing. If you split your lasers, pop them along each arm, bring them back together again. If there's a relative shift in the length of the arm, you'll see that in an interference pattern That's the sort of basic idea. There's a hell of a lot of technology behind it. So that's LIGO. Here's what they're claiming. This was I thought this was probably the best slide to pick. So there's, I think it's the Washington detector that's 6 months behind the other one, but I think that they are supposed to be switching on this year, and they say that there's a possible detection in 2015. I think they're hoping that this year is going to be the year they detect a gravitational wave. When they sort of, have a bit of downtime, do a post-mortem, clean things up, the second run, that's when they're starting to say they're pretty confident they should see something. So it's really about sensitivity, because these are very small effects, and signals. Is there a signal that's like a smoking gun? You see something, or you hear, I think they make the analogy with hearing more than seeing. Is there a particular waveform that's characteristic? So when you get a merger of either neutron stars or black holes or one of each, it's obviously quite a dramatic gravitational event, and it has a very sort of characteristic signal. There's a sort of little noise that suddenly comes up and chirps, so there's a very characteristic kick that's, with a characteristic frequency dependence. So those are the sort of things that they're looking for. And these distances are sort of how far out they think that, they're effectively going to be able to see these events happen with confidence. So that's sort of summarizing LIGO, which is saying, I think we really are, if they don't see something within the next sort of 3 or 4 years, we should be worried, okay? There's something happening. So I think that's an exciting experiment. This is just summarizing. I put this up because it was actually not so much because it was something that was new, but because the experiments that they do are so beautiful and so precise. These guys, and it's everybody but the person talking, my apologies to Adelberg, are telling us about precision tabletop tests of gravity. So it's called the Earthwash group, and the idea is that we can certainly watch things fall down, but these guys watch things fall sideways. So they're kind of looking at comparisons between inertial. So if you rotate stuff, you can see the inertial mass come in, and the gravitational mass, which pulls down. And they do this with beautiful precision. So, the problems that they have are, if the gravity field is not uniform. And it's quite funny seeing some of the data where, there's definitely a lot of noise around sort of rush hour, this sort of thing. So it's quite fascinating, all the problems that they have. And so here is just, again, to give an impression of, the sort of precision that they can have. So here they're kind of ruling out, I think, additional forces. So here they're looking. Remember when I talked about the brain world corrections? I said people often talk about Yukawa corrections, e to the minus mr type corrections. So here they're ruling out sort of the massive part of the attraction to the Newtonian sort of attraction between two bodies. I put this one in because I think this is interesting. It's something really different. It's not only interesting from a gravitational perspective, I think it's interesting from a quantum mechanical perspective. So this is an idea coming from atomic physics, cold atoms. People now can have quite a lot of control. They can cool atoms down sort of practically to nanokelvin, and they have a lot of control over the actual position of the atoms, so they can get wave packets of these, wave packets which are strongly localized and can manipulate them. So this is sort of quite an interesting concept. And not only is it sort of testing gravity, it's also testing quantum physics over not just tiny scales, but large scales. So this is sort of meant to sort of give an indicator of the wave packets of these atoms, and the idea of these sorts of experiments is that they get these rubidium atoms, cool them right down, and then they sort of make a fountain of the atoms, so they throw the atoms up so that the atoms are sort of moving under the effect of gravity. But this particular atom has two close by energy states, which can be manipulated into each other by a laser transition. So this is sort of saying you've got a laser transition, and by the amount of time you switch your laser pulse on for, you can control how much the atom makes a transition from energy state 1 to energy state 2. Now, the two different energy states fall at slightly different rates. And so what this means is that you get a sort of split, but it's not a split of atoms. The atoms are actually in a superposition of these energy states, so it's really very quantum mechanical. So if you think about it from a path integral perspective, you're sort of throwing up an atom, or you're throwing up a bit of wave packet, you split it, the slower bit, starts to be retarded more quickly. The faster bit goes up further. When it reaches the top, you do a complete flip, swapping 1 and 2. They fall down, start to come together again, and then at the end of the experiment, you flip them back and you interfere. So you're looking at, you've got sort of various contributions to this phase shift, but it's hoped that it's some part of that contribution, because they've gone along different geodesics, is going to give you an information about gravity. So this is still at a sort of, I think, more of a test bedding downstage, but I think this is interesting because this is sort of combining aspects of not quantum field theory, this is real sort of, cold quantum Schrödinger type of quantum physics over macroscopic scales and possibly looking at gravity. So that's one to watch for. And then finally, and unfortunately Avery hadn't put his slides on, so Avery is the guy doing the imaging of black holes, so I had to go and poach a few things. This is an image of the center of our galaxy, and what you're seeing here are the positions of various stars. So this is why we believe there's a black hole at the center of the galaxy, because they're going round, look at that orbit there, how eccentric it is. They're going around this central object, which is dark and very, very heavy. So here, Avery's proposing to do imaging of the black hole, and this is what a rotating black hole, what the accretion disk is going to look like. I'm trying to play it, I'm not sure, there we go. So this is, you see the way the light is kind of doing funny things and then forming all these rings. This is from this strong lensing effect. So there's obviously, this was just heuristic, there's a lot of modeling gone in there. Once they've got the modeling of what it looks like in theory, they've then got to model what you're going to see. And what they're doing that with is a sort of radio, at the radio frequency, with this huge, sort of with various radio telescopes at different parts of the world. So they've got a very long baseline, and so that's hopefully going to enable them to actually image something that small at the center of the galaxy. Right, so that was just to give you an impression. That's where gravity's going. Those sort of, we've got hopefully a gravitational wave detector. Maybe here at perimeter, someone's going to actually see the black hole at the center of the galaxy. I think they're claiming they're pretty much there. And I'm kind of excited about this idea of atom interferometry. So I think gravity is actually becoming quite an interesting experimental science, and not just so that you can use Google to find out where when you're trying to get back home from the pub late at night. So, and of course, thank you for sticking with it, and well done. So.